So, welcome to this new class. So, we will just review the last class in which we discussed first the intrinsic and extrinsic defects, the temperature dependence, and then we looked at what are the possible units for defect concentration. And then we moved on to an important topic of defect equilibria, which is basically the purpose of this showing this was to basically establish the criteria that we can treat these defect reactions just like chemical reactions. So, the thermodynamics of defect reactions can be treated in a similar way as thermodynamics of a chemical reaction in dilute solutions. So, let us say you have a chemical system with various number of species with their respective moles, and then we worked out what was that Gibbs-Duhem equation. Following that, we could work out what was the we could work out that the K, which is the reaction constant, which is nothing but a ratio of product of products, product concentrations divided by ratio or activities divided by product of concentrations of reactants. Now, so this is K, but we also saw that K is also equal to K naught exponential minus H naught by K T or R T, which explains the temperature dependence of K. So, this helps us in establish the relations later on when we want to make a defect. So, you can see that defect concentration now not only will depend upon the temperature, and now we will establish that it also depends upon things like oxygen partial pressure. So, then we looked at the defect equilibria in stoichiometric oxides, considering defect reactions like chemical reactions, where we assume that defects are very small in numbers. Hence, these can be considered as solute in a solvent or dilute solution. Solid can be considered as a dilute solution, where solvent is the host lattice and solute is the defect. So, first we took the case of Schottky defects and considered an example of MO, and in that we worked out the reaction constant, and we find that there is no temperature dependence of concentration in case of Schottky defects, and concentration is purely dependent upon temperature and magnitude of delta Hs. So, and this typically happens at intermediate partial pressures of oxygen, and in these ranges your VO is equal to Vm. So, similarly the same was true for Frenkel defects as well. Again the concentration is independent of partial pressure of oxygen, and it is dependent upon temperature and defect formation energy. So, both the formalisms are similar, with the conclusion that in case of stoichiometric solids, the defect concentration does not depend upon the partial pressure of oxygen, it only depends upon the temperature. Because and then we looked at what is the equilibrium concentration in non-stoichiometric solids. So, first we considered the case of oxygen deficient oxides, example of, let us say, taking example of MO1 minus X. So, some oxygen is missing from the host lattice, those sites are empty. So, when oxygen, so first case we took was when oxygen vacancies dominate. In such a situation, your the defect reaction can be written as like this, and so O gives rise to VO plus half O2 plus 2 electrons, and then we worked out that using the charge neutrality condition, Ne is equal to 2 VO, and we can also write the defect. We can also write the reaction constant, which has dependence not only on concentrations and also on partial pressure of oxygen. And if we just interchange various equations, what we work out is the concentration of defects or electrons is proportional to P(O) to the power minus 1 by 6. Temperature dependence is of course given by K. Now, at a fixed temperature, what it means is that, so not only the concentration will depend upon K, that is temperature, as exponential minus 1 by 2 to the power 1 by 3, it will also depend upon partial pressure of oxygen to the power minus 1 by 6. So, if you plot these, so VO is plotted as a line with slope of minus 1 by 6. We know from charge equality that Ne is equal to twice of VO. So, any line would lie just on top of this VO line, and that will be 2 of VO. And then we did the similar analysis for conditions when metal excess prevails. for an oxygen deficient solid. In such a condition, your MIs dominate, and again you can write the equation for K, and again you can see that Ne is proportional, Ne and Mi both are proportional to P to the power minus 1 by 6, and again you can plot the charge concentration, defect concentration as a function of partial pressure of oxygen. So we were here now. Now, the next case that we will take is in this lecture. So, the next case now we will take is case 3 or C, I do not know what we used. Let us see what we used in the previous slide. C. So, I will just rub 3, case C. Okay. So, in this case we will take simultaneous presence of. Now, so far we have considered that only one kind of defect can be present at a time. Now, in this case we will consider simultaneous presence of two defects, which is oxygen vacancies and metal interstitials. Okay. So, this is the again for oxygen deficient solid. Now, examples of such a scenario, this is a very practical scenario. So, examples of such scenario is oxides like TiO2 or Nb2O5. So, all these oxides show not only oxygen vacancies, but also metal interstitials, and this is simply because metal ion tends to be smaller. Titanium is a smaller cation. So, as a result it tends to go to vacant interstitial sites. Now, so we will take an example of, so consider an oxide, let us say MO2, and this oxide has doubly charged oxygen vacancies, that is VO dot dot, and it has doubly charged metal interstitials, that is Mi dot dot. So, we have not taken completely charged metal interstitials for convenience, and I will explain you what the convenience would be, because if you take this Mi 4 dot, then you may not appreciate the exercise that we are going to do. So this is the situation. So, for the first scenario, when you have so what is the defect reaction for the formation of these vacancies? So, oxygen at oxygen site goes out, giving rise to two vacancies plus half of oxygen going out, and as a result you create 2 electrons. So, this is the reaction for oxygen going out, or other reaction in case of metal interstitials would be MM plus 2OO, because it is MO2. So, you have Mi metal going to interstitial site, sorry, I will just take, so it is not completely ionized, I will only take 2 electrons. So, compensating that you will have 2 electrons and both the oxygens go out. So, that maintains the site balance. So, this is the situation. Now, let us say that defects are smaller in number as compared to host lattice. We can assume that MM is equal to OO is equal to 1, assuming that it is a dilute solution. So, now we can write the defect reactions for we can write the reaction constant, and now reaction constant, assuming that MM and O were equal to 1, K1 for the first reaction would be, so I can write this as KVO, let us say. Okay. Just to avoid the confusion, I will just let us go to previous slide. So, this is This is, let us say, reaction 1 and this is reaction 2. So, that makes it better. So, for reaction 1 we can write K1, and K1 will be equal to VO multiplied by PO to the power half multiplied by NE square. Okay. And for reaction 2 we will have K2 which is equal to Mi multiplied by PO2 multiplied by Ne square. Okay. So, these are two expressions that we get. Now, what is the electrical neutrality condition? That says that in the reaction 1 number of electrons Ne is equal to 2 of VO, and for the second case, so this will total basically, and for the second case, so from this is from reaction 1, and from reaction 2 Ne is equal to 2 Mi, right. So, if both were simultaneously present, then Ne would be equal to 2 VO plus 2 Mi. So, the concentration of Ne would depend upon the total concentration of these two. So, let us say we take two limiting cases. Okay. Limiting case 1. Now, this limiting case 1 is so you can have both VO and Mi in various proportions. So, we are taking two extreme conditions. One condition is when VO is large in quantity, another condition is when Mi is in large quantity. So, we will take first case, which is VO is much larger as compared to Mi in concentration. So, if that is the case, then we of course, the reaction 1 would be more appropriate reaction. So, that gives us the concentration of VO is equal to half Ne is equal to, because from the electrical neutrality condition, in that case, in such a situation, Ne will be equal to 2 VO. Okay. So, VO will be half Ne, which will be equal to your K1, you can work out from this expression, K1 to the power 1 by 3 to the multiplied by PO to the power minus 1 by 6. So, you just go to previous expression. So, this is what you have, K1 is equal to VO PO to the power half Ne square. You replace the expression for Ne, which is equal to 2 VO. So, it will become 4 VO square. So, if you take PO2 on the left hand side and just invert the equation, then it will become VO cube is equal to K1 by 4 multiplied by PO to the power minus 1 by 2. And then you just, so VO cube was equal to that. So, when you want to take for VO, the right hand side will become to the power 1 by 3. So, this is the expression for VO you get here. Okay. Now, what will be the concentration of, now we are saying that VO is very large in number, but still what is the concentration of Mi? So, Mi concentration will still be given by reaction 2, but in that reaction now Ne is governed by concentration of VO. So, Ne is no longer a function of Mi. So, from reaction 2 we know from reaction 2's rate constant or reaction constant or equilibrium constant, we know that K2 was equal to Mi into Ne square multiplied by PO2. So, here this so you replace Ne is equal to 2 VO, because in this condition Ne is not dependent upon Mi, it is only dependent upon VO, because VO is much larger than Mi. So, now K2 will become Mi dot dot multiplied by what is Ne square. So, it will become 4 into K1 to the power 2 by 3 into PO to the power minus 2 by 6 into PO2. Okay. So, now all you have to do is that you have to rearrange. So, Mi will become K2 divided by 4 into, so this will become 1 by 3. So, this will be PO to the power 2 by 3, which on the other side if it goes, it will become PO to the power minus 2 by 3, and this, so K2 divided by 4, and then this becomes 4 to the power 2 by 3 divided by K1 to the power 2 by 3. So, I have just taken everything on the other side and written expression for Mi dot dot, which will reduce to K2 divided by 2 K1 to the power 2 by 3. Okay. So, this is basically 4 to the power 1 by 3. So, 4 to the power 1 minus 4 to the power 2 by 3 will be 4 to the power 2 by 2 will be equal to 2 to the power 2 by 3. So, K2 into K1. So, Mi, so in this regime, when VO is much larger than Mi, then VO is equal to K1 by 4 to the power 1 by 3 into P to the power minus 1 by 6. So, VO varies, log VO varies as with the slope with respect to PO2 with the slope of minus 1 by 6. On the other hand, Mi varies with the slope of minus 2 by 3. And what is the boundary condition? The condition beyond which this is valid. So, we are saying that if you want to determine that partial pressure of oxygen beyond which this is valid, in that case we are saying that since VO is greater than Mi. Okay. So, what is VO? VO is K1 by 4 to the power 1 by 3 into PO to the power minus 1 by 6 is greater than K2 divided by 2 K1 to the power 2 by 3 multiplied by PO to the power minus 2 by 3. So, this is the condition that we establish, and so if you now rearrange this, what you will find is that PO2 is greater than K2 divided by K1 square. Okay. So, this is the pressure beyond which this condition will satisfy. Okay. So, this was case 1, limiting case 1 when VO is greater than Mi. Second case we will take is when Mi is greater than VO. So, we have determined this condition. So, naturally this condition will prevail under this. So, PO2 has to be lesser than K2 by K1 square. You can verify that using again this equality when you calculate the concentration. So, now we know from so first we will calculate what is Mi now. So, from reaction 2 we know K2 was equal to Mi multiplied by Ne square into PO2. So, Mi now will be equal to, and under such a condition Ne will be equal to 2 of Mi, okay, because it is much more larger than VO. So, Mi Mi under such a condition will be equal to half of Ne, which is equal to K2 divided by 4 to the power 1 by 3 into PO to the power minus 1 by 3. This now you can do. I am not going to do the whole exercise. So, all you need to do is that you need to put this expression here and just rework the parameters on either side to work out an expression for Mi in terms of PO2. So, this is one expression, and now for calculating VO, we know that K1 was equal to VO into Ne square multiplied by PO to the power half. And now this Ne now is equal to 2 of Mi. Okay. So, we will just move to next slide. So, we know that K1 is equal to VO into Ne, okay, Ne square. So, Ne square will be 4 Mi square, and Mi square will be K2 divided by 4 to the power 2 by 3 multiplied by PO to the power minus 2 by 3 multiplied by, if you go to previous expression, previous page, K1 was VO, we have replaced Ne with 2 Mi, and Mi is equal to this. So, we have just replaced this. So, K2 by 4 to the power 2 by 3 into PO to the power minus 2 by 3 multiplied by 4 multiplied by PO2. Okay. So, now if you work out the expression for VO in terms of PO2, what you will find is VO is equal to K1 divided by 2 K2 to the power 2 by 3 into PO to the power 1 by 6. So, we can see here that in this regime Mi has a pressure dependence of minus 1 by 3 to the PO to the power minus 1 by 3, and VO has a dependence of PO to the power 1 by 6. So, again now you can calculate the boundary. So, we know that since Mi is larger than VO, and just put in the value of Vi and Mi and VO, and what you will find is K2 by K1 square is greater than PO2, which is nothing but you worked out from the previous expression. So, now you can so here you can see that VO increases as the partial pressure of oxygen decreases, and but at different rate as compared to previous exercise. Sorry, VO increases as you increase the partial pressure of oxygen up to certain point, and then it decreases when VO is much larger. So, we will just now plot this. So, this is log of any kind of concentration. So, which means concentration will mean your Ne, VO and Mi, and this will be your PO2. Okay. So, the boundary we get it at, so let us say we start at an arbitrary point, and this boundary is equal to K2 by K1 square. Okay. So, now what we see is that PO2 larger than K2 by K1 is when K2 by K1 square is larger than PO2, which means the smaller PO2s. In that case, what we have is our VO varies as this. So, this will be plus 1 by 6 for VO. Okay. And how does VO varies? How does the VO vary after when PO2 is larger? In that case, it varies as like this. So, this will be minus 1 by 6. This is the VO line. Now, how does, let us say, blue line. Now, how does Mi vary? Mi in this region, if you go to previous slide, it varies as -1/3. If you go to previous slide, it varies as -2/3. So, now if we just take it, so it varies at -2/3 here, and in this region it varies at -1/3. So, this will be your Mi, and n is nothing but, if you want to plot n, so n is nothing but in this region 2 of Mi, and in this region it is 2 of Vo. So, up to this point n is equal to 2 of Mi, and in this region it is equal to Ne is equal to 2 of Vo. So, this is kind of an equilibrium diagram where you get a boundary, the transition point and the conditions away from the boundaries in both the directions. So, in one condition your Mi is the dominating defect, in another condition your Vo is the dominating defect, and in between both of them exist together. So, basically what it means is that you start drawing the lines from the far off regions and then let them meet at the junction, which is nothing but P02 is equal to K2 by K1 square. So, I hope this gives you an idea about how to establish these various equilibrium conditions. You can take single defect situation, you can take multi defect situation, and see how they coexist under various conditions of partial pressures of oxygen. So, next we will take into account what is the scenario in case of metal deficient oxide. So far we have considered scenarios of defect, we have worked out the defect equilibria only for stoichiometric only for oxygen deficient oxides and stoichiometric oxides. Now, what is remaining is metal deficient oxides, and we will do it very briefly, because now that you understand the fundamentals of how to work out defect equilibria in case of oxygen deficient oxide, the approach is similar in case of metal deficient oxide. So, we will only take one case in such condition. So, here now let us see how we had the numbering. So, this is case C. So, A, capital A. So, we will take capital B here, and we will take defect equilibria in metal deficient oxides. Okay. So, again consider, for example, MO as model oxide. All right. So, as now assuming complete ionization of vacancies, for the formation of metal vacancies, what you write is half O2. Now, this will happen in, for example, COO, FeO, etc. So, you write half O2 is equal to OO. So, oxygen has gone to oxygen site. In order to maintain the site balance, you need to create a metal site. However, there is, since it is metal deficient, that will be metal vacancy, and that would be doubly charged, and that would be compensated by creation of 2 holes. And the equilibrium constant for this will be K to be equal to OO multiplied by Vm dash dash multiplied by NH square divided by PO to the power half. Now, we know that from electrical neutrality condition, NH is equal to 2 of Vm. So, as a result your K will become, and also assume that and OO is equal to 1, because it is very large number. So, as compared to defect concentration, so it becomes K becomes Vm double dash multiplied by NH square multiplied by PO2. And so, now what you can do is that K in such a situation will be NH, if you replace by 4 Vm cube multiplied by PO2, sorry, PO2 to the power minus half minus half. So, Vm double dash, so just see there was a mistake here, it should be, so if it goes there now it will become K by 4 to the power 1 by 3 into PO to the power 1 by 6. So, this is the expression for Vm, and this is also equal to, since NH is equal to 2 V, so this is NH by 2. Okay. So, this is the expression for pressure dependence for whole concentration. So, if you just draw a plot here, the plot would be something like this. So, you have log of concentration and this is PO2. So, if this is your, oops, sorry, the positive slope. So, if this is your Vm line, then your whole line will be right on top of this. Vm. Okay. So, this is how it will vary. The scales are arbitrary, we will see they are relative to what is beyond or what is after. So, what is before or what is after. So, we will see that. So, this is the case in case of metal deficient oxides. When metal vacancies are dominating defects, you can do the similar exercise for conditions when. So, I will just leave it to you. For example, I will just mention the condition here. Condition A, when Vm dominate, and I will leave it to you as an exercise. Solve it, do the defect criteria calculation for condition 2 when OI dominate, and condition C when mixed presence of OI and Vm. So, the analysis is very similar to what we have done in previous case for oxygen deficient oxides, and this would be similar in case here as well. Now, if you remember in the case of yes, in this case we chose an oxide MO2 with when we took simultaneous presence of oxygen vacancies and metal interstitials, we took an oxide MO2, that was for a purpose. What happens is that in these materials, if you had Mi completely ionized, which means Mi 4 dots present, or if you had taken an oxide MO with completely ionized defects, then you would not see this transition. As a result, when you make the measurements, now these, as we will see later on, these are all all these plots which I am plotting at the moment, they can be obtained by making conductivity measurements as a function of pressure, oxygen partial pressure. So, when you make those conductivity measurements, you are not able to ascertain, you won't be able to get this sort of those sort of differentiation which you get in these cases. So, this kind of analysis is applicable in cases where it is very explicit that how what kind of defects are present at what kind of oxygen partial pressures. So, just looking from the analysis or the derivation point of view, it is easy to derive it for cases like these, where such as in MO2 you have Mi dot dot etc., but it does not work, the approach, similar approach does not work for instance, if you want to do for MO where both the defects are completely ionized, or even for MO2 where both the defects are completely ionized. So, one has to be careful. If you want to go into details of this, you can go through the book of Perkofstad, which is non-stoichiometry in oxides, which I have listed in the bibliography. So, but this is a very useful approach. You can see where you can find out the differentiation and where you cannot. So, that you can work out yourself by taking various examples of various oxides. So, now, so this is as an exercise I left it to you. So, basically work out defect equilibria in metal deficient / oxygen excess oxides in under following conditions. Now, the third case in this series would be intrinsic ionization. Now, intrinsic ionization, as we have seen, it has nothing but formation of electrons and holes. So, basically you have this band gap of the material, any oxide. So, the electrons from valence band, so this is your valence band, this is your conduction band. So, electrons from here jump to valence band, gives rise to electron in the conduction band and hole in the valence band. So, this leads to formation of electron hole pair, and the reaction would be null electron and hole, and equilibrium constant for this would be E dot H, and since Ne is equal to NH, Ne is equal to NH will be equal to Ki to the power half. So, you can see in such a condition, when this happens at moderate partial pressures of oxygen, under such conditions you can see that Ne or NH is only dependent upon Ki, which is temperature dependence, as you know, and it is independent of partial pressure of oxygen. So, now what we will do is that so far what we have seen is that we have seen oxides of specific kind. We have considered cases of metal deficient, we have considered the cases of oxygen deficient, we have considered the cases of stoichiometric conditions. Typically, as you can intuitively think that metal deficiency or oxygen excess would tend to occur at higher oxygen pressures, oxygen deficiency would tend to occur at lower oxygen pressures, and intermediate oxygen pressures would determine the stoichiometric condition. Now, what we will do is that we will consider one particular oxide and we will look at the defect equilibria for this particular oxide under three conditions of oxygen partial pressure. Okay. So, basically, so we will consider defect equilibria for an oxide MO, for MO under number 1 low PO2, number 2 high PO2, number 3 moderate or intermediate PO2, which is typically in most cases atmospheric pressure, intermediate PO2. So, this condition would typically determine deficiency of oxygen this condition would typically determine excess of oxygen, and this condition would typically determine stoichiometric condition. Okay. So, now deficiency of oxygen will also mean excess of metal, and excess of oxygen will also mean automatically, not automatically, but it would be metal vacancy. So, assume that the defects which are present are either oxygen vacancies or oxygen interstitials, and let us say both are doubly charged, absolutely completely ionized. Okay. So, let us say what are the defect reactions first. So, first we will see, let us change the color. So, defect reactions. So, first we will write for low PO2 case. Okay. So, at low PO2 I am not considering M. So, if this was VO, then you would have complementary defect MI, or you can have VM. So, we are just considering oxygen at the moment. You can consider others as well, but let us not complicate, let us just simplify, otherwise it becomes little complicated. So, just to simplify, we have chosen only one kind of dominating defect in one region. So, at low PO2, the defect reaction would be OO, which means oxygen present in the lattice going out, giving rise to oxygen vacancy plus 2 extra electrons. Now, assuming OO was equal to 1, almost equal to 1, and so this would be, so we can write K for this reaction. So, let us say this is KVO. So, KVO would be PO2 to the power half multiplied by VO dot dot multiplied by NE square. So, I am not writing in terms of NE, I am just writing the whole without replacing for NE. So, this is the first expression that you get. Okay. Now, the second expression we will write at high PO2. So, at high PO2 the defect reaction is half O2 is equal to OI plus 2H. Okay. And as a result, the reaction constant you can work out as KOI to be equal to OI dash 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 multiplied by NH square divided by PO to the power half. And third condition is, oops, change the order here, A, this should be B, and this should be C, intermediate. What am I writing? PO2. So, under intermediate PO2 there are two possible scenarios. Under intermediate scenario is, so number one is intrinsic ionization, giving rise to creation of electrons and holes. So, the reaction in this case would be E plus H. So, under such a condition Ki would be equal to Ne multiplied by Nh, and the second condition that is possible is So, either you can have intrinsic ionization which dominates. So, stoichiometric defects could be of electrons and holes, or the stoichiometric defects could be Frankel defect or anti-Frankel defects. So, the reaction here would be OO is equal to OI plus VO. So, basically what you can see here is the defects that we have considered at higher and lower PO2s, they have to be in accordance with the defects that are going to be presented in stoichiometric conditions as well. So, that you get a continuity in the defect concentration as a pressure function of partial pressure of oxygen. So, you can see that intuitively now if you had chosen Schottky defects here, Schottky defects would give rise to Vm and Vo. So, you would have continuity for a Vo, but Vm would not have. So, either you replace OI here with Vm. So, if you had Schottky defects dominating in that intermediate pressure range, in that case you would have to choose Vm in the higher pressure regime. So, you understand what the logic is. The logic is whatever defects you choose in the intermediate, low and high pressure regions, there has to be continuity in the defect concentration. So, if you choose one particular kind of stoichiometric defect in stoichiometric region, then that particular defect grows or reduces in the concentration at higher or lower pressures. So, that makes sense, and that also makes our life little easier. So, for this reaction we can write Kf is equal to OI multiplied by VO, and so from these 4 expressions for, so this is let us say 1, this let us say is 2, this let us say is 3, and this let us say is 4. So, if you combine these expressions, combining above expressions gives us Kf multiplied by Ki square is equal to Kvo multiplied by Koi. Just a second, should be in sub. That is easy to verify, you can do that yourself. So, this would be question number 5. Now, what we will do is that we will work out the limiting conditions for each of these cases, which means if we are making a plot, for example, of PO2 versus concentration. So, of course, this is the low pressure regime, this is the high pressure regime, and this is the stoichiometric regime. So, we know that these are 3 regions, but we do not know where the boundary occurs. So, we need to define the boundaries, where these boundaries are. So, what basically it would mean is how we would define boundaries are, this region would be a region when you have OI a lot greater than VO. Okay. In this region, we will assume that VO is a lot greater than OI. And in this region, we would assume either intrinsic ionization or anti-Frankel defects. We will take both the cases, which one each of domination of each of these, and we will see how these concentrations then vary as a function of partial pressure of oxygen and which defects dominate in which region. So, we will finish here. We will take these limiting conditions in the next class, followed by we will calculate the concentrations of defects in each of these regions based on these limiting conditions, and then we will draw the plots of concentration of defects versus partial pressure of oxygen, which are also called as Brewer's diagram. These are very important diagrams, because at any given temperature you can see what the defect concentration versus partial pressure of oxygen is going to look like, and these plots also replicate when you measure electrical conductivity versus temperature. You do not know the relation of electrical conductivity with respect of, to partial pressure of oxygen or concentration yet, but as we will see later on that these plots are very useful to know, because you get the similar plots by plotting DC conductivity versus partial pressure of oxygen as at a given temperature. So, we will do all this in next class, and then we will move on to next topics after this. Thank you.